First of all, we should isolate the alternating part from the non-alternating part by calling an to be equal to 1 over 2n plus 1 factorial. Okay. All right. So this is sort of like not different from the previous example. So number one, the limit of 1 over 2n plus 1 factorial. Well, remember that a number factorial is that number going down all the way to 1 multiplied all together. So if n is larger, that factorial is going to be even larger. So 1 over infinity is going to be 0. So the first condition is met, right? And second condition, I'm going to use the same idea here, 1 over 2n plus 1. So I'm going to look at an plus 1, so 2n plus, so 2 times, in other words, 2 times n plus 1 factorial, okay, which is equal to 1 over 2n plus 3 factorial, right? Okay, that is less than or equal to, obviously, 1 over 2n factorial, because here you're dividing by a bigger number, okay? So this equality is just obvious, true for all n. Okay. So the second condition is all met. So then I can go back and conclude that this is a convergent infinite series. And this is a pretty fast convergence. So here is the minus 1 to the n to n plus 1 factorial. As you see that the difference between the two consecutive terms for an is always negative. Okay, that's a decreasing behavior, and the limit is always 0, as you see. And in a very fast fashion, the partial sums converge to somewhere close to this number. Okay? As you see that the blue dashed line is the number that the series converges to, and that's pretty fast. Okay.